All right, so we're continuing looking at the charged rod. This is a one-dimensional rod that's charged with uniform charge density, and we're trying to calculate the electric field at somewhere, some point along the x-axis. Um, at the end of the day, we want to be able to get an electric field, an expression for the electric field that works for anywhere along the positive x-axis. So that's what we're trying to do. And in the last video, I discussed that what we're doing here with this rod is splitting up into these little charges, where in each little charge here, each little elemental piece of charge or a little infinitesimally small piece of the rod, we have a charge dq inside this little red square here, charge dq, and the length of this rod, or the length of this part of the rod, we call it dl. Okay, and we talked about that we're going to split it up into electric field in the x direction and electric field in the y direction, and then here's our expression for dE. All right, same equation as we saw earlier in chapter 22 and in chapter 23. K dq, instead of q, we put as dq over r squared. Okay, and I also wanted to mention here that this is uniform charge density, so the total charge over the length. It's just a ratio of charge to length. So we can even put dq over dl, right? That's still that ratio of charge to length. So it's just that when I write like this, it's specific to this block here. Okay, so what do we go next? How do we actually get the expression? Well, we're gonna start looking at these components, right? Dex and Dey. And what's very helpful once we start thinking about what are we plugging in for our components here, is looking at the symmetry of this problem. What we have here is a rod, uniform charge density, so that means there's equal amount of charge up here and equal amount of charge down here. And all these are giving us our electric fields. Now, if there's a same amount of charge, same distance, right, same amount of charge and the same distance here, that means the electric field here is also symmetric. If it's symmetric here with the charges, it's going to be symmetric here with the electric fields. So what that tells me is that the electric fields, I have as much electric field pointing up as I do pointing down. And if I think about the components for all these vectors, split them out to components, I have an equal amount of electric field going up as I do going down, and I have an electric field going to the right, right? There's no electric field going to the left. So that tells me two things about my components. One thing, for the y components are going to cancel. If I have a whole bunch of electric fields, going up, and then I have a same amount of electric field going down, right? Those two components there are going to cancel, right? And this is because of our symmetry, because we have this rod is symmetric across the x-axis. So on top of the x-axis and below the x-axis, right, it's essentially the same, right, symmetric. So our y components will cancel there. So that means dE net or E net y, oops. Let's see here. E net y is 0. Again, because you have equal amount of electric field pointing up as electric field pointing down. Okay. Now, in one of my classes, someone said, "Well, this, oops, maybe it was, I can't pick that point." I guess I can't pick it. Let me do it this way. If the point of interest was moved up here, right? Do I still have, is that symmetry true? No. If we're now interested here, the electric field in the y does not cancel out, only here, because the symmetry is matched with our rod. Okay, so only at this point here is the electric field cancel. If I look off center here, the electric fields in the y direction will not cancel. So the electric field in the y direction here does cancel. Okay, so that leaves only really the x components. So what I want to do is just focusing on the x component, let's get an expression for Dex. Okay, so we're going to focus just on one of these charges. Let's focus on this one. let's focus on this one right here. So I'm gonna draw a line here, connecting, oh, let me make that a little bit thinner. Okay, so I'm pretty much gonna erase all these other electric fields that we're looking at and just focus on that one. So we're only looking at the electric field here coming from this dq, this little piece of charge. Okay, and I want to get the x components. Well, this is just like any other vector. The dE that you see on the screen here could be split up into components. Oh, let me make that a little bit. So dE, that would be my dEx here. And dEy. Now we already said the dEys are going to cancel once you include all the other electric fields. But I will draw it here. Okay. How do I get dEx? Usually we have an angle, right? If we're talking about components, we'll define some kind of angle. Let's define that angle. Okay. So in order to get dEx here, I would have to do my hypotenuse, which is dE times cosine theta. And I know what my dE is, k dq over r squared. And cosine theta though. Okay, so cosine theta, I don't want to keep this as just cosine theta, because theta is introducing another variable to our problem. Right now I'm going to have to consider how my charges are changing the angle. But we could represent this theta in a different way. Look, that would be the same theta, wouldn't it? Right, those two are vertical angles. So if I focus on this triangle here, draw a little triangle, whoops. So we have this distance here, which I'll just call x. And then we have this distance here, which I'll call y. Okay, and then my hypotenuse, which is r. Okay, so if you see that triangle, let me talk about the hypotenuse. The hypotenuse we can easily solve for, right? Hypotenuse is just, you use Pythagorean theorem there, and you get square root of x squared plus y squared for your hypotenuse. Okay, so we have here for the x component cosine theta. Well, what's cosine theta in terms of this triangle? Well, remember cosine theta is adjacent over hypotenuse. So I could substitute in for cosine theta x, which is my adjacent side of that triangle, over my hypotenuse. There you go. Okay, now there's a couple, so there's that cosine theta. Now I have my x component here, dEx. But there's still a couple of things that are a little bit vague. So for example, let's look at, I have k. K is just our constant that we talked about, Coulomb's constant. dq, well, what's dq? Well, we could define dq in terms of the charge density. Okay, so down here, I said charge density, you could do charge over length or dq over dl, which if I rearrange that, rearranging it and solving for dq, I get lambda dl. I can even be more specific than that, because if you think about what dl is, what's dl? dl is this vertical distance of my little charges here. It doesn't really matter which charge you're looking at, but it's this vertical distance that we just call dl, but it is along the y direction, isn't it? All these are, this distance here is along the y-axis. So instead of writing it just dl, I could be even more specific and call it lambda dy. Okay, so let's keep going here. For dEx, I'm gonna have k. What's my dq now? dq is lambda dy. And then r, well, what's r in my equation, right? Anytime when we have our Coulomb's law equation, what's r? Well, r is a distance from your charge. In this case, we're looking at this charge right here. this dq, to your point of interest. So we're looking at this distance, which is our hypotenuse. So my r is going to be x squared plus y squared. And then I have my cosine ratio here, x, my opposite, my adjacent over hypotenuse. Okay, so that gives me dEx, right? Just to simplify it. So I have integral, and what's my dEx? Well, just simplify this here. So if I simplify that, I get k lambda x over, I'll multiply the denominators there, x squared plus y squared, that we get 3/2 there for the exponent. And then we have our dy. Okay, so we got an expression that we can now integrate, right? We can integrate this. The only thing that's left before we actually integrate are the limits, right? What are we gonna put in our limits here? Okay, so if we're looking at this rod, our limits are what's the highest value for y that we're gonna get? Because remember, if we're looking at these different charges, to get all these electric fields that I drew earlier, we're looking at essentially these different charges here, right? Different positions. Well, what's changing as we look over these positions? Well, the thing that's changing here is y. X is staying the same, right? No matter which little box you're going to look at, that distance x stays the same here. It's a distance that y is changing as you look to each charge. So when we're integrating, right? Notice this is dy because that's a quantity that's changing here. What is the largest value of y that we're going to have, and what is the most negative value of y, or the lowest value of y? And I think I don't know if I said this in the previous, I think I did. In the previous video, I had a length here actually that I forgot to write here. Okay, the length of the rod we call L, right? L. So if that's L, what's going to be my largest value for y? Well, my largest value y is for the charge that's at the very, very top of this rod. So that would be a value, a y value of L over 2. That's my upper limit. Now what's my lower limit? My lower limit is the charge that's all the way on the bottom of the rod, down here. Well, what is the y value for that position, right, at the bottom of the rod here? Well, the y value for that is negative L over 2. Okay. Now, of course, you could even simplify this even further and use symmetry one more time and say that you're only going to integrate from L over 2 to 0, and then just multiply your final answer by 2. If you're thinking that that will work out, that will give you the right answer, but I don't think you need to do that. Okay, I mean, whichever way, I don't think it simplifies a whole lot. Maybe it does. Okay, so let's see here. So now we have our integral. This is our integral here. Now it's just a matter of solving this integral. Right? We did all the physics parts here, but all this was we're using physics, we're using electric fields and all that, and we got this expression. Now we just use our math. We use our math to integrate this. Well, let's take out all the constants here. Take out the constants. Let's say take out k lambda. K and lambda. Okay, so factor those out. And then I'm going to integrate here x over x squared plus y squared. Right. Well, this is dy. So I'm just setting out my integral. I'm taking out my constants. I did leave x in there. Actually, I could take out x if I wanted to. So let's just take out x here. And again, negative L over 2 to positive L over 2. Okay, so I just have to take this integral. Oh. And this is dy here. Let me make that a little bit neater. It's just getting too messy here. dy, and then positive L over 2. Okay. So how do I integrate this? All right, well, I'm not going to work out the integral. So the way you would do this, you know, if you're in a calculus class, is that you would do a trig sub. And the trig sub you would do is that you set y equals to x tan theta, which means dy would equal x secant squared theta, d theta, and you'll make that trig sub. Okay. So what I don't want to work out through all the algebraic steps of plugging that in, rearranging it, using it. You have to use a trig identity. You guys could look that up if you want and do it. And if you have questions, you could always ask me. But what you would get here after you do all that, you get E net x. Remember, there's all in the x direction here. Would equal k lambda, right? There's our constants out in front. And you will have here, as a result of integrating, y over x times square root x squared plus y squared. And then you have your limits. Okay. Okay. Let's see here. So we have our limits, and then now this is just the process of doing all this algebra, plugging in here and plugging your limits, or L over 2 for y, negative L over 2 for y, and then simplifying your limits. Okay, so this is what I get. If we do that, okay, and remember, this is our only electric field. We don't have a y component. Our y component was 0, right? So we had 0 y component. Everything here is our actual electric field. It's our x direction, but it's what we actually have. Okay, this is our whole the electric field from the rod. So if I simplify what's this in the brackets here, once I plug in my limits, this is what I get: k lambda L. Okay, and then I have 1 over x times square root. So I can fit this in here. X squared plus L over 2 squared. Okay, and this is in the I hat direction. Okay, so this is the electric field from my rod at any point in the x-axis. Okay, so quite a bit there, quite a bit in order to get there. Right, we had to start by analyzing a segment of charge. That's really starts here. We split up this rod into segments, and once we get into segments, we start analyzing, you know, the electric field, analyzing what the dq is, right, and that's where the charge density comes in, and then we analyze the symmetry, right, and that really helped us. If we didn't analyze the symmetry, you would have this, you wouldn't know this was 0. So you would have pretty much, you would have to do this whole thing again for the y component, and you would end up with 0. You would get the same result, but you would just have to do double the work in order to prove to yourself that it was 0. Okay. All right, so let me summarize here, kind of like the steps. Okay, so steps in analyzing continuous distributions. Okay, so I have a couple of steps, or it's more than a couple, but pretty much breaks down what we did. So I'll say the first step here, step 1, we did obviously draw the figure. and include axes, like your y-axis and your x-axis, and your point of interest. Okay, because that's pretty much the very first thing we did, right, in the last video. We drew that and explained where the x-axis was, explained where the point of interest was. Okay, then split the object, whatever object we're looking, in this case a rod, but split the object into elemental charges. Those are those infinite, spell that. Very small charges. Okay, that's where those red boxes were that I drew. Let me expand this. Okay, so if we go back to the previous slide here, these are my elemental charges, right? We couldn't do this without thinking of this rod as being made up of a whole bunch of small charges, of these little charges taking up a little space here. Okay, so let's keep going. So split out into elemental charges. Okay, then we specified, I'll put this, take into account symmetry. So by taking into account symmetry, that it's going to tell you if any of those components go to 0. Right? And like I said, it saves us a lot of time. Imagine if we didn't know that, if we didn't take into account symmetry, we would have essentially 2 equations that we'd have to solve for. Right? We would have to do this E net x, and we would have to do this E net y. Okay. Okay. So once you take into account symmetry, then define your DE and its components. Okay, what do I mean by that? Well, this is where the DE, right here. You're pretty much always going to start here, or you're eventually going to use this, and all these problems that you guys are going to be doing. Okay, you're eventually going to have to use that at some point. It's just like, what is your DQ? And I explained in the last video that your DQ can change depending on what your geometry is, what's your object, but you pretty much have to find your substituting your DQ. And then once you do that, then you find, like what we did, we found DEX, right? And we didn't have to find DEY, but that will be step 4. And then once you do that, you define that, and then you have to integrate. So you have to do the math of it. All right, so that's essentially what we did here in our steps. If you kind of review how we got this final answer with our electric field, it followed those steps to get there. All right, now what I want to do here, I'm not quite done with this rod. I want to analyze this, and I'll show you a different way of writing this, because this K here, this constant, there's another way of writing this constant. So I want to talk about that, and also want to talk about this equation in general. So this is our electric field for a finite rod, right? It's taking a certain length out, and we're bisecting this rod, so we're in the center of the rod. Okay, now I want to take a look at, which I guess let me do it in the next slide. Okay, so we calculate the electric field for a finite rod. Let me put it this way: find the electric field for an infinitely long rod. So what would be the difference? Well, we had a rod that that was just a certain length. Okay, so this was a certain length, L. But what if that rod was extremely long? So instead of just a rod here, what if it was, what if I made it like this? So I could where it was very, very long, almost essentially infinite, right? So, and what I mean by infinite, like you say, well, how is that practical? You never have infinite rods. That's not real. But what I mean by infinite, if you're looking at a point right here, and that distance here, let me see, this distance right here, let's call that x, right? That's what we called it earlier, x. If that distance x was so much smaller than the actual length of the rod, right? Because this length would be very big. Okay, if that distance x was so much smaller than the rod, so we're looking at when L is much, much greater than x. So from that perspective, that rod essentially is infinity. Okay, so you're so close to it that rod looks to you, and it goes on forever. It goes on forever downwards, goes on forever upwards. So it's an infinitely long rod. Okay, so it does come up if we're talking about the like, let's say an electron. An electron is, you know, a certain distance from a very, very long wire. Well, if that distance is, we're talking like millimeters even, and we're talking about a 15-meter long wire, well, that rod or that wire is acting approximately like a infinite rod. So that's just the application. We could approximate very, very long rods to be infinite. And if we do that, what is the electric field for it? So let's start with what we had earlier. Let's start with the E field of a what we had earlier of a finite rod. Okay, so for the electric field for the finite rod, we got this: E equals K lambda L 1 over, I'm trying to remember what it was. Let's see, K lambda L 1 over X square root of X squared plus L over 2 squared. I hat. Okay, so our overall electric field from that finite rod was something like this, right, pointing to the left. Okay, so there's a couple things I'm going to do differently in order to get our infinite rod. One thing is not as crucial, but comes up a lot. There is a different way of writing K, or Coulomb's constant. So instead of talking about just this value for K, is related to something called the permittivity of free space. Okay, so this symbol here. We call it the permittivity. See if I can remember how to spell it. Free space. And it's essentially telling you that how easy it is for electric field to go through empty space. Now the epsilon 0 has a number. Okay, epsilon 0 is 8.85 times 10 to the negative 12. So 8.85 times 10 to the negative 12. And the units are just the inverse units of Coulomb, or of the Coulomb's constant. So Coulomb squared over Newton meter squared. I believe that's correct. Okay, so that's epsilon 0. Now epsilon 0 does change if we're not talking about free space. So if we're talking about the, if we're talking about charge inside water, or a charge in an insulator or something like that, that epsilon 0 is going to be a different value. But for free space, for vacuum, we use this number. Okay, so this relates this K to epsilon 0, and the reason why I'm introducing it to you now is because, well, a couple of reasons. One, it does give us some nicer equations by plugging this in for K. And also in chapter 24, we deal with epsilon 0 explicitly. So it comes up quite a bit. All right, so here's a different way of writing Coulomb's constant. All right, and now I'm going to write this E, not only with Coulomb's constant here, but I'm going to change it algebraically. what I'm going to do is factor out this x squared from my square root. I'm going to factor out x squared from here and factor out x squared from there. Even though it's sorry, not x squared. I'm going to factor out the L over 2 squared. Okay, I'm going to factor that out. So if I do that, factor out L over 2 squared from here, which will make it 1. Factor out L over 2 squared from here, which means I have to put in a 2 over L squared. I get an equation here. So let me show you what I mean. So I get lambda over, and I'm going to have 2 pi epsilon 0. Okay, now I made a substitution here for k. I substituted the 4 pi epsilon 0. What happened to the 4? Well, because I factor out the L over 2. I get a 2 that comes out when I factor that out. So I'll get 1 over x times square root 4x squared over L squared plus 1. Now, if you do the algebra here, factor out L over 2 squared, like I told you, from inside the integral, you will see, and substitute this, okay, for substitute 1 over 4 pi epsilon 0 for k, you will see that you get the same equation, right? There's a little bit of algebra there, some manipulating, but the reason why I want to do it, right? I was fine with this equation, by the way. This would have been a perfect equation to get your answer. But I wanted to do this because going back to the infinitely long rod, what I'm saying for that is I'm taking L to go to infinity. Okay, if I want to see what happens when L goes to infinity, I need to rearrange this. So I rearranged it like this, and you can kind of see what's going to happen when L goes to infinity. This term here goes away. Okay, so when L goes to infinity, we get a different equation for our E. Lambda over 2 pi epsilon 0. And all we're left with, because if L goes to infinity, what happens to this? Well, that just goes to 0, doesn't it? If you have infinity in the denominator. So now we're left with 1 over x. Oops. And it's still in the same direction. Okay. So this is the electric field for an infinitely long wire. And we come across pretty often, like I said, if we're talking about relative distances, that wire is going to be, we could approximate very long wires as infinite wires if we're talking about this small distance here. Okay. Now one more thing before I wrap this up. What's kind of common here is not a little difference in notation here. What's commonly, we don't use x very often. Usually you'll be labeled as r. Okay, which means that this will be r. Now r doesn't mean radius, it just means distance from the wire. Okay, so I just wanted to note that because if you're looking at your textbook, I believe it'll have 1 over r in there. All right. So if we plot this for the electric field from an infinitely long wire, you're going to see a 1 over r relationship. Yeah. So this would be your electric field here and your distance from the wire. And what we see is a 1 over r relationship. So as you go further and further from the wire, the electric field does drop off, but not as fast as a point charge, right? Remember what the point charge was? The point charge would have dropped a lot faster. Something like this. Because the point charge is 1 over r squared. Okay, so the electric field for a point charge drops off pretty quick. For the electric field from an infinitely long wire, right, we saw this 1 over r relationship. So it does drop off, but it doesn't drop off as fast. Okay, mainly because you have more charges spread out. You know, all the electric field over here and electric field over here. It's all building up to give you a electric field going to the right. Okay, so quite a bit of algebra. If you ever want to see me go from here to here, you want to see the algebra, just stop by my office hours and I'll show you. But it's all I did was plug in for k, factor out L over 2, and this is what resulted. All right, so that's our first exposure there to continuous charge distribution. In the next video, we'll be looking at a ring of charge, and we're going to do a similar approach where we essentially we're going to be following these steps here that I had earlier to analyze a ring of charge. So a different geometry, but the same idea behind it. All right, so we'll do that next time.